Hey everyone, welcome back. So today we're going to go over Chapter 18, Gasoline Engine Operation Parts and Specifications. So in this lecture, I'm going to go over and I'm going to discuss the engine construction, the engine's purpose and function, energy and power, and engine construction. I'm also going to explain parts and systems and also explain the four-stroke cycle operation. I'm going to discuss engine classification and construction. I'm going to explain engine measurements and discuss compression ratio, torque, and horsepower today. So, first, engine purpose and function, energy and power. So, what the basic function of what an engine does is we convert heat energy of fuel into mechanical energy, which propels the vehicle. It is power the air conditioner and power steering, and then also produce electrical power needed throughout the vehicle. So in ways, what we're doing is we're actually taking we're taking heat and combustion and turning it into a mechanical movement, and then we're using that mechanical movement to actually create other energy. So as we have the engine rotate, we're also going to be rotating the alternator, which then when that alternator rotates, it's actually going to go ahead and create electricity to charge the battery, which then goes ahead and powers all the electrical needs in the vehicle. Internal combustion occurs within the power or the combustion chamber. It creates mechanical force, which is converted to mechanical power. Engine construction overview. So let's first go over the basic parts of an engine itself. So first, we're going to go ahead and have the engine block. The solid frame constructed from cast iron or aluminum that provides the foundation for most systems. The rotating assembly, which is the crankshaft and the connecting rods and pistons, and cylinder heads, which seals the tops of the cylinder and contains the valves that allow the air and fuel into the cylinder and the exhaust out of the cylinder. So think of the block as the main structure, the main core of what an engine is, how an engine is created. Then the rotating assembly is what actually will help create the pull in of air and fuel into the system. And then the cylinder heads are what actually close it off and allow the pressure to build up so we can have a complete combustion, which then starts the process all over again. So the rotating assembly for a V8 engine that has 8 pistons and 8 connecting rods and 1 crankshaft. So we're going to have one solid crankshaft in the center, and attached to that is going to be our 8 pistons because this is actually a V8 design. And each one of these pistons is going to have a connecting rod, which then connects to the crankshaft itself. A cylinder head with 4 valves per cylinder, 2 intake valves which are larger and the 2 exhaust valves which are smaller. So if you look at this picture here, they actually have the 2 intake valves that are in there right now. So the reason why they are larger is you want to be able to get more air and fuel into the actual combustion chamber. More air and fuel means a cleaner burn and also more power. And then obviously we have the 2 exhaust ports here. When the valves open up, it allows the exhaust to actually come out. Engine parts and systems. The intake and exhaust system. When you think of intake, think of it as you're breathing. When you're breathing, you're inhaling, you're actually pulling air into your lungs. For an engine, you're actually pulling air, and we're also going to be mixing fuel with it. Now, depending on what type of fuel delivery system is going to determine when the fuel is actually being introduced into the air itself. For carbureted systems, it actually happens inside the carburetor. As soon as air passes through the carburetor, it actually mixes with the fuel and then gets dispersed throughout the intake manifold. With multi-port or port fuel injection, is actually going to be directly into the actual intake manifold ports just before it goes inside the combustion chamber. And then we actually have direct injection, which injects fuel directly into the combustion chamber. It doesn't actually get mixed in prior to going in, pass through the intake valve. Cooling system is used to control the engine temperatures. Remember, we don't want the vehicle to run too cool or run too hot. I think I said in the last lecture, we have more modern vehicles that actually run at a higher temperature than most older vehicles. Say like 60s vehicles, 70s, they actually run a lot cooler, about 190 to 200 degrees. Most vehicles nowadays run closer to about 215, 220 degrees. The reason why is we actually get better vaporization of the fuel and we actually get a good cleaner burn. Lubrication system used to lubricate moving and sliding components to reduce wear and dissipate heat. So not only is oil there to actually help lubricate and keep parts running nice and smooth against each other, but it's actually also there to absorb a lot of heat. The vehicle does produce heat. You actually have a small explosion in each one of the combustion chambers. Now that small explosion, the heat has to go somewhere. It doesn't all dissipate through the exhaust. It actually gets absorbed in through the cylinder walls and it also gets absorbed in through the oil. So it's actually a way to actually help cool as well as lubricate. Fuel and ignition systems provides the needed fuel and spark to the cylinder. Obviously, we need some type of fuel to burn. And then depending on how much fuel is needed is going to be controlled either via the carburetor, or we actually control it via the fuel pressure or the fuel injectors. And then also we need a way to ignite that air and fuel, so we have what is known as the ignition system. It is what generates a high voltage spark between the spark plug and actually will help ignite the air and fuel mixture inside the combustion chamber. The coolant temperature is controlled by the thermostat, which opens and allows coolant to flow to the radiator when the temperature reaches the rating temperature of the thermostat. Like I said, we want a vehicle to get up to operating temperature, and if we have it take too long or too slow, it actually can cause the vehicle to not necessarily run rough, but it can cause problems later on down the line. So what happens is this thermostat traps the coolant inside the engine block and allows it to stay in there and warm up a lot quicker. Once it gets up to operating temperature, this little guy has wax pellets inside, and once they actually start to melt, it'll actually open up the thermostat and allow the coolant to actually go back into the radiator and start circulating. So when the thermostat is stuck closed, or when a thermostat is closed, it doesn't allow coolant to exit. It only allows it to stay inside the engine block to keep it actually in there to warm it up a lot faster. And then once it reaches operating temperature, then it's going to start to circulate. A typical lubrication system showing the oil pan, oil pump, oil filter, and oil passages. So we got to get the oil from the pan, correct? We need to be able to pump it out of the pan and circulate throughout the rest of the system. So we actually have all these small oil galleries, but also as parts start to deteriorate, oil starts to get older because it's being used, we actually need to find a way to filter it out, hence the oil filter. So when you're doing a regular oil change, all you're going to do is you're going to drain out the oil, you're going to change the filter, and you're going to fill it back up obviously with new oil. You never want to reuse old oil because it doesn't have the, it's going to sound funny because it's food related, it doesn't have the nutrients needed to actually clean, or not to clean, but to lubricate properly. So we definitely want to put new oil when we're actually doing an oil change, and we also want to replace the filter. 4-stroke cycle operation. So we actually have 4 strokes per complete combustion, or for a complete combustion cycle. The first stroke is actually going to be the intake stroke. The piston moves down, drawing air and fuel into the cylinder. The compression stroke, the piston moves up in the cylinder, compressing the air-fuel mixture. The power stroke, the spark ignites the air-fuel mixture, forcing the piston down. The exhaust stroke, the piston moves up in the cylinder, forcing the exhaust gases out of the cylinder. When they mean stroke, is actually, they're talking about one movement of the actual connecting rod and the piston. And so if you're starting up at the very top, one stroke is actually going all the way down and staying there. That's one stroke. So when you actually come back up, that's another stroke. So if you think about it, it's actually 180 degrees, 180, so it takes 720 rotations for one complete combustion, or one complete 4-stroke cycle. So the 4 strokes of the engine are shown below. Now, key placement or key position of the valves is very important when it comes to this setup, or when it comes to combustion. For the intake stroke, obviously because it's called the intake stroke, guess which valve is going to be open? That's correct, the intake valve. Air and fuel are going to be pulled in because as this piston's coming down, think of an engine as a large air pump. As it's pulling down, it's actually sucking air and fuel in. So as it sucks air and fuel in, because the intake valve is open, it's going to be pulling it and drawing it in. As it starts to come down and start to make its way back up, both valves are going to be closed. So now we actually have a closed container, and when it starts to come up, we're going to start compressing that air and fuel. The reason why we want to compress the air and fuel is it creates a more volatile combustion, meaning we actually can create a larger explosion by compressing. If we were to just go ahead and pull it in and ignite it down at the bottom, it'll burn, but it's not going to burn with the same power that a compressed mixture of air and fuel will actually burn. So now that we're coming up, we're compressing. So we're taking that air and fuel, we're squeezing it, we're trying to get it in a small little pocket. When we get in that small little pocket, boom, we spark the spark plug. Now that we spark the spark plug, it's going to push that piston back down. That explosion is going to actually start to expand because we're creating gases in there. We're starting to burn it. and as it starts to expand, it's going to push that piston back down. When it starts coming back down, it's going to rotate one more time, and as it comes back up, we're going to have the exhaust valve open at this time. When it's coming up, it's going to push that burnt air and fuel and make its way out through the exhaust manifold and out the tailpipe. So now, once we're done with this one, it's going to close up as we reach top dead center, and we're going to start it all over again. So now we're going to do intake stroke again. So when you think about a 4-cylinder, 8-cylinder, 10-cylinder, so every single stroke is actually going on at a certain time. But remember, when this one's going on the intake stroke, you're actually going to have another cylinder doing the intake stroke as well, or you're going to have one that's they're going to be on separate stages because of the amount of cylinders. Excuse me. So what are the strokes of a 4-stroke engine cycle? So let's go ahead and go over the first one, intake. What does the intake do? Yes, you're going to have the intake valve open. It's going to be drawing air and fuel in. Now that it's coming back up, which stroke is it? Compression stroke. Yes, correct. As it's coming back up, it's going to compress the air and the fuel mixture, and then it's going to go ahead and go top dead center. It's going to ignite, and then what's the next stroke? Yes, the power stroke. Power stroke is going to actually cause it to expand, come back down, and as it's coming back down, once it's reached the bottom dead center, it's going to start making its way back up, and then it's going to do the exhaust stroke. Engine classification and construction. So, number of strokes is 4. Cylinder arrangements. We have inline 4, 5, and 6 cylinders. So that means that each one of the cylinders is actually right next to each other. We have a V-type 4, 6, and 8 cylinder, which means that the cylinders are going to be opposed towards in pretty much about a 45-degree angle from each other. And then horizontally opposed 4 and 6 cylinders, where they're often referred to as boxer engines. Those boxer engines usually in Porsche, they're also in Subarus, Volkswagens, and all those pistons actually point away from each other in this direction. Engine classification and construction. Longitudinal mounting, engine mounted parallel with the length of the vehicle. So now they're talking about you're looking in the front of the hood, or you're looking down the front of the hood. The engine is actually going to be pointing towards the rear of the vehicle. So the front of the engine is actually going to be in the very front of the car. The rear of the engine is going to be at the rear of the car. A transverse mounting engine, or engine is mounted crosswise. I don't know why they use the word crosswise. I'd rather say sideways. So take that same engine, mount it sideways. That's mostly for front-wheel drive cars and some all-wheel drive cars. Valve and camshaft number location. You have pushrod engine, a cam and block design. You have overhead valve, single overhead cam, and dual overhead cam. They actually misspelled this one, is incorrect. It's not supposed to be overhead OHC because that's actually overhead cam. This one actually should be OHV, so overhead valve. Type of fuel, we use gasoline, E85, M85, natural gas, propane, and diesel. So even diesel vehicles are still a 4-stroke vehicle. There are some 2-stroke diesels out there, but they're not really used for regular, normal, day-to-day vehicles. It's usually big, large commercial vehicles. Cooling method, we use liquid or air, and a lot of air is actually for more older vehicles, like the old school Porsches and Volkswagens. Those are all air cooled. The type of induction pressure, naturally aspirated or turbo or supercharged. We'll go over a little bit of turbo and superchargers. I don't know if we do it this module, but we definitely will go over it when you guys are here. And engine rotation direction, principal end of the motor, flywheel end of the motor, and then non-principal end of the motor, which is the front of the engine. Cutaway of an engine showing the cylinder, piston, connecting rod, and crankshaft. So now you can see you have your crankshaft right here and it rotates. Now, when you think about the position in which the crankshaft is mounted onto the connecting rod is mounted to the piston or the crankshaft, is it directly in the center? Because if the crankshaft starts rotating, is this going to go anywhere? No, it's actually got to be offset. And when you offset it, it actually creates almost like not a teeter-totter, but kind of like a bicycle crank, because the center point here, and then you have your pedals. You're actually transferring power back the opposite direction. If you're transferring power through the crankshaft through the middle, it's actually causing that up and down motion. If you think about the pedals go down and up, down and up. So in this same concept, as it rotates, it's actually going to cause it to go like this in this general direction, right? And the cylinder is what guides the piston up and down. So we actually we turn a rotating motion into an up and down motion. And at the same time, we're connecting the crankshaft to a camshaft at the top. And when we connect them together, as this one rotates, this camshaft is also going to rotate. and causes the valves to open and close at predetermined times. Automotive engine cylinder arrangement. So now you can actually kind of see the breakdown. So you have 4-cylinder, 5, and 6 cylinders. And these are all going to be inline engines. And then we have V4, and then V6, and then also V8 engines as far as the number of cylinders. And then you have boxer engines. So you can see these are actually mounted sideways rather than, wrong direction. Sideways rather than a V pattern or a inline pattern. A longitudinally mounted engine drives the rear wheels through a transmission, drive shaft, and differential assembly. So as you can see, the engine is actually in the same direction as the transmission, and as how the power actually gets transferred through the vehicle to the rear wheels for this design. And for a transverse, you can see it's actually mounted sideways. Now, they have made vehicles before. Well, obviously this is a transverse mounted engine, and it's going to be sideways. You're going to have front wheel drive. They have made transverse mounted engines, a forward longitudinal engine with front wheel drive still. If you look at, I believe it's a 68 Cadillac Eldorado. It's actually a giant V8 engine, but it's mounted the same direction as this one, but it's still front wheel drive. And it's a crazy design on how they actually created the transmission. I believe it has 2 drive shafts that come out and then 2 differentials that go and split. So if you guys want to do a little extra credit, look up that vehicle and actually send me some information and see what you guys actually find about it. It's a 68 Cadillac Eldorado, if I'm not mistaken. Cutaway of overhead valve V8 engine showing the lifters, push rods, roller rocker arms, and valves. So we haven't really gone over the valve train. We're mostly talking about the bottom end. So we're definitely going to go in and I'm going to talk to you guys about how this design actually works and how it all works in unison. Single overhead engines usually require additional components such as a rocker arm to operate all of the valves. Dual overhead cam engines often operate the valves directly. So dual overhead cam actually rides directly on top of the valve rather than using a rocker arm and using a single camshaft which will open and close each of the exhaust and intake valves. A dual overhead engine uses a camshaft for the intake valves and a separate camshaft for the exhaust valves in each cylinder head. So with this design, you can actually have one camshaft just strictly exhaust, one camshaft strictly intake. Now the downside to this is obviously there's more wearable parts, but at the same time you do get a lot more power output from a dual overhead cam than you do a single overhead cam. A rotary engine operates on a 4-stroke cycle but uses a rotor instead of a piston and crankshaft to achieve intake, compression, power, and exhaust stroke. This design here is actually more for the Mazdas. Mazda use rotary engines. If you guys look up like really old rotary engines, and they also actually, take that same engine, they really build them up. They sound really cool when they're idling, and they do have a lot of power output, but at the same time, they also kind of stumble a little bit. They're not really all that reliable. Now this one, what happens is you have an intake port. So this thing actually rolls. You guys remember those spirographs? There's actually the little gears, and you would take a pen and you actually create like a pretty cool design. It kind of works in the same concept of how it rotates. It actually rotates like this, kind of like how an egg rolls. When you have the egg rolling, as it comes down, it's going to pull in the air and fuel, it's going to compress, it's going to ignite, and then once it ignites, it's going to swing back around and then actually pump out the exhaust. So each one of these points creates either pressure or it creates suction. So as it rotates through, it's going to suck air and fuel in, it's going to ignite, okay, and then it's going to create the power stroke and then force the air out. So it doesn't actually go up and down, it actually moves in a circular motion. Inline 4-cylinder engine showing principal and non-principal ends. Normal direction of rotation is clockwise as viewed from the front or accessory belt non-principal end. So the front of the engine is pretty common for all vehicles to go ahead and rotate clockwise from the front, but if you're looking at it from the back of the engine where the flex plate or where the flywheel is, it's going to be rotating counterclockwise. So remember, if you're looking at it through the front, it's clockwise. From the back, it's counterclockwise. Engine measurements. You have bore, which is the diameter of the cylinder. Stroke, which is the distance the piston travels from the top dead center to bottom dead center. Displacement is the cubic inches or cubic centimeters of the volume displaced by all cylinders. And the conversion to liters, cubic inches divided by 61.02 equals liters. So I'm not going to get too deep into this just yet. I do want to actually do this a little more not necessarily one-on-one, but a little more group effort with trying to go over and give you guys how to actually calculate displacement, and then also how to find out what bore measurements and stroke measurements are. So we'll go ahead and skip over that just for a little bit. So the distance between the center line of the main bearing journal and the center line of the connecting rod journal determines the stroke of the engine. So let me see if they... Okay, so now I'll at least go over how we determine what the stroke is and how we determine what the bore is. So at top dead center, when this piston is all the way up, we're going to measure the distance from there all the way down to when the piston is at bottom dead center. So that's the amount of stroke. That's the total up and down movement of the piston. And then for bore is actually the diameter of the piston itself. So if you have a 4-inch bore and then a 4-inch bore and then a 4-inch stroke, that's actually the measurements for a small block 350. That's a 5.7 liter. It's either 4 or 4.030, which is it's an overbore, and it's usually a 4-bolt main crankshaft, and we'll go a little bit more over that. I like using the Chevy small block V8 as a good reference point because it's a very universal engine. There's a lot of them out there. I mean, it's a lot easier to get your hands on a small block 350 and just learn to build one of those engines and put that in, a project car that you have. It's a very good overall easy vehicle or engine to work on. So what is the bore of the engine? That is correct. It is the diameter of the cylinder. It's the size of the piston itself. And then the stroke is the length that the piston travels up and down. Compression ratio. The difference in volume when the piston is at the bottom dead center, or BDC, versus top dead center. Changing compression ratio, which is you can do using head gasket thickness or increasing the cylinder size. So, compression ratio. If the compression is lower, you're going to have lower power. You're going to have poor fuel economy, easier engine cranking. More advanced ignition timing possible without spark knock or detonation. If compression is higher, you have higher possible power, better fuel economy, but it's harder to crank the engine, especially when hot, and then less ignition timing required to prevent spark knock or detonation. So if you have a low compression engine, it's a lot easier to start. You're not going to create a lot of power. It's just a very economic and reliable engine. Once you start getting into a higher compression ratio, that's when you're going to start to not necessarily run into problems, but you're going to have a lot more stuff to actually have to deal with to create the maximum power output, but also prolong the life of the engine itself. Compression ratio is the ratio of the total cylinder volume when the piston is at the bottom of its stroke to the clearance volume when the piston is at the top of its stroke. So you have, let's see, so you have your volume clearance, which is going to be 1, and then you have the cylinder volume, which is actually 8, so you have 8:1 compression ratio. And I've actually seen a lot of vehicles run with really high compression where they're actually running, anywhere from 16 to 17:1, which is a lot of pressure being built up inside that engine. And that's why, if you guys ever watch, race cars, or especially drag racing, they rebuild their engines after every single run. And I'm talking, they pull the engine all the way down to the bare block, they take the pistons out, they take the crankshaft out, all the way down the bare block, and then they build it back up. The reason why is because of the amount of air, fuel that is getting crammed into that engine and how much power it makes. It does so much damage because it's only going 1,000 feet. And they only need it to run 1,000 feet. It needs to turn on, do a burnout, and run 1,000 feet. And that's why we have to actually rebuild, because such a high compression ratio and so much heat and so much fuel go through that engine that it actually destroys destroys the engine after every run. So they actually have to take it all apart, check, make sure they can replace with new pistons. They replace, they rebuild the cylinder heads, and by the end of the race, the spark plugs already have melted away, the actual point. So it's not even running off the spark; it's running off the temperature inside the combustion chamber. That's why, in order to shut these vehicles off, if the throttle sticks, they have to shut fuel down. They can't just shut down the spark because there is no more spark. It's actually just high temperatures inside the combustion chamber. Combustion chamber volume is the volume above the piston when the piston is at dead center. So the amount of area inside here where air and fuel can actually be inserted in, and once it's actually under top dead center, this is actually a combustion chamber volume. And it's usually measured in cc's. If you hear like, oh, let me get 10 cc's of this, medicine or whatever, it actually is measured in cc's, and Obviously, the larger area you have, the more air and fuel you can get in, but obviously your compression ratio lowers. So there's a lot of give and take when it comes to that, unless you go with a bigger piston and you have a higher combustion chamber volume. Torque and horsepower. A rotating torque is a rotating force that may or may not result in movement. The amount of force multiplied the length of the lever through which it acts. Horsepower, the power required to move 550 pounds 1 foot in 1 second. Horsepower and altitude. Horsepower is reduced as altitude is increased. SAE says that naturally aspirated engine loses 3% of its power every 1,000 feet or 300 meters of altitude increase. So if you take a vehicle that's up in Colorado, obviously there's a Mile High City or something that's over a mile from the sea level, the vehicles are going to run, I wouldn't say worse, but they have a potential to run worse being at higher altitude than a vehicle down here on the shore in California. Torque is twisting force equal to the distance from the pivot point times force applied expressed in units called pound-feet or foot-pound, pound-feet or Newton meters or N-M. So if you have 1 foot of actual wrench or wherever the pivot point is, so you have your nut or bolt here, and then you're applying 10 pounds of force here on this end, you're about a foot away, so that would be 1 foot-pound. What is the definition of torque? The amount of force multiplied the length of the lever through which it acts. So that was just a quick little lecture. I didn't want to go too in depth with the top end or the valve train. The reason why is we're going to have actually an entire chapter for it. I'm going to have 2 chapters up tomorrow, which is the 24th. So be ready for those lectures as well. I just wanted to go over this one real quick. I was trying to make up for last week's lecture. I missed this one, so let's go ahead and continue. You know, we're doing a great job. Let's keep doing what we're doing. If you guys have any questions, please let me know. You guys all have my phone number. You guys have my email, all right? And I'll talk to you guys later.